Okay, so now I want to investigate what is the order, the accuracy order of these approximation that we made. So let's examine that. In order to examine that, what I'm gonna do is looking at the higher order terms and other equations, right? So we only had up to F2 equations, so we have to go further to understand and to find out what is the actual order of accuracy for this approximation. So for example here, if you remember, we only got to Fm, right? But we also have higher order terms that we did not include and we have not investigated yet. So we have to look at those terms like Fm plus 1 and see what is the order of the accuracy for this approximation, okay? So let's calculate F3 here. We went up to F2, if you see. So let's go to F3 and see what it is. So F3 is gonna be what? Is gonna be gamma I minus 1 times, and you have it here, this to the power 3 over 3 factorial and this to the power 3 to 3 factorial, right? From this equation here, you can say that. So we have minus 2 delta x to power 3 over 3 factorial plus gamma I minus delta x 3 to power 3 over 3 factorial plus gamma I plus 1 again times 0. So this is going to give me what? This is going to give me, I can just factor out 1 over 6 here from the 3 factorial, and from the gammas here I have delta x squared, right? So I have it here, so I'm going to also factor this out here. So I'm going to write it as 1 delta x square, 1/6 over delta x square. So gamma I minus 1 is going to be what? Is going to be the first term here times gamma I minus 1. So gamma I minus 1 is just 1 over delta x square, which we have already factored out here. So here the only thing that remains is minus 8 delta x cube. The second term is going to be what? Is going to be plus minus, yes, it's going to be, we have a minus 2 here, so I'm going to just write it down. So minus, like plus minus 2 times minus delta x cube, right? So it's going to give me, this is going to be plus 2 and this is going to be minus 8. So it's going to be 6 minus 6 delta x cube over delta x square over 6. So this is not going to be 0, right? So it's not going to be 0, right? And therefore this tells us that this approximation is first order, or order delta x, right? Because if you kind of simplify this, you will get something on the order of the delta x, right? So this is going to be order delta x, this approximation. So let's see something interesting. You might have, if you had seen this before, this is a center difference scheme. You might have expected that this should be or second order, like order delta x squared. But why it is order delta x? The reason is we are expanding this over xi plus 1. So let's see if we use this approximation. So we use this approximation for d square u dx square evaluated at xi. What's going to happen? What would be the order of this approximation? So if I calculate that, f3, so f3 is going to be 1 over 6 delta x squared. And let me do it here. Let me just write it a little bit down because I want to do something here. So f3 is going to be 1 over 6 delta x squared. So let's see. So the first term is going to be what? It's going to be xj, which is xi minus 1, minus x star, which is now going to be xi. Okay, so it's minus delta x. So I'm going to have minus, instead of minus 2 delta x cubed, I'm going to have minus delta x cube, right? So this represents that one, plus then I have the second term. The second term is going to be what? xj, which is xi now, minus x star, which is xi. So it's just going to be 0. So it's going to be what? It's going to be gamma I times 0. So it's going to be plus minus 2 times 0. And then the third term is going to be, so this represents this. The third term is going to be xj, again xi plus 1 minus xi. So it's going to be just delta x, right? This is just delta x to power 3, or delta x cube. So as you, so it's going to be delta x cube. So as you notice, what? This is 0, and these two terms cancel out, right? This one cancels out with this one. So I can just write that this equals to 0. Thus, in this situation, in this condition, f3 is 0, and this approximation is second order, or order delta x square for d square u over dx square evaluated at xi, or at I. Right? So as you see, it is the same approximation, but evaluated for the function at two different points. It can give us two different orders, right? So the order, the accuracy of the order of the accuracy might be different. And in center differences, this is usually the case in center differences. Sometimes if p equals to m plus 1, in center differences, this can be order delta x squared. But generally, as I said, if your number of points is just m plus 1, which was the case here, the number of points were 3, and the order was 2, then the order of the approximation is generally order delta x, right? Okay. So this was the main example, and we found the order of accuracy for this approximation, which was order delta x. And just as a remark, I want to say that, so this was, if we want to find, this was an example in which we try to find an approximation based on this general method that we introduce, okay? So sometimes in the questions or in the problems, you might see that the approximation is given, and then the question wants you to find the error, or to find you the truncation error. So in those cases, you don't necessarily need to do these calculations. There is also another way to do that. If you don't want to write all these things from scratch, you can just with the Taylor series or Taylor expansion. So if the approximation is given and the order of accuracy or sometimes truncation error is south, you can just use Taylor series. So by Taylor series, you can get the same answer or the same solution as what we got. Okay, so now I want to introduce some standard finite difference approximations, okay? So standard finite difference approximations okay. So assume that grad xi, the backward difference, forward difference, delta xi, center difference are all equal to each other and equal to delta x. Okay, so now I want to introduce some of the kind of well-known finite difference approximations that you might see. Okay, so the first one is for the first order, and there are many tables for this that you can take a look at that, but I'm gonna just say some examples. So du over dx evaluated, so the first derivative evaluated at point xi can be approximated as a forward difference, which we talked about is ui plus 1 minus ui over delta x. This approximation is order delta x, and it is forward difference, right? So the other one we can have is ui minus 1 over delta x. This approximation is also order delta x, and this is backward difference. The other approximation for the first derivative is ui plus 1 minus ui minus 1 over 2 delta x. This approximation is order delta x squared, which is different than the previous ones, and it is central difference. Okay, we can have more complicated approximations, like by using more points and also increasing the accuracy. For example, this one is minus ui plus 2 plus 4 ui plus 1 minus 3 ui. So this uses 3 points over 2 delta x, and this is also order delta x squared and a forward difference, but with 2 points rather than just 1 point. Okay, we can even make it more complicated by using 4 points to get higher accuracy. So Then we are going to have minus ui plus 2 plus 8 ui plus 1 minus 8 ui minus 1 plus ui minus 2 over 12 delta x, and this is going to be order delta x 4. Okay, so I just want to note that first, this is a central difference, right? So this is central difference. And the other thing I want to note that, as you see, we are able to increase the accuracy to higher orders, very, very accurate, like as we go higher and higher orders. But then you need to use more points, as you see here, from I plus 2, I plus 1, I minus 1, and I minus 2. And the other note that I want to make is you can get all these based on these approximations based on the general formulation, general scheme that we mentioned here. And I solved an example for it here, right? So you don't need to actually memorize all of these. Maybe just some simple ones like this, but all the other ones like this one, which is kind of more complicated, these you can just obtain based on that approximation, general approximation method that I introduced. Okay. Another way to approximate these first derivative is using what we call a variable weighting between these methods, right? So what we are going to do is we are going to combine these methods and we are going to use a variable way of doing that. So the first one is when we use a forward difference with central difference. This is called a variable upstream weighting. So I'm going to use alpha ui plus 1 minus ui over delta x, and then I'm going to add to that the central difference. So I'm going to add it 1 minus alpha ui plus 1 minus ui minus 1 over 2 delta x. Okay, and this is called variable upstream weighting scheme, right? And you can have similarly, you can combine like the backward one with the central difference here, and then you can get a variable downstream weighting, right? Instead of this one, we can just write a backward difference. Okay. So these are some general ways, standard ways to approximate the first order, the first derivative. And then let's look at the second derivative. When we have d square u over dx square evaluated at xi, this can be approximated as ui plus 1 minus 2ui plus ui minus 1 over delta x squared, and this is going to be order delta x squared, and this is central difference. So this is the one that we obtained, if you remember, in the example. And we can have more complicated ones similarly, and we can obtain those based on the scheme that we showed. So for example, this one, ui plus 2 plus 16 ui plus 1 minus 30 ui plus 16 ui minus 1 minus ui minus 2 this over 12 delta x square, and this is going to be order delta x to the power 4. Right, so it's a higher order scheme that can be used. Okay, so these were some general standard finite difference approximations that we introduced, and in the next lecture, what I'm going to do, I'm going to solve an example in which we are going to find the truncation error of the advection diffusion equation for a particular finite difference approximation. So we are going to find a truncation error of a finite difference approximation. Okay, so this is for the next lecture, and for that I'm not going to use this method that I've used, and I'm going to use the Taylor series, similarly to this point that I try to make. If the approximation is given and the order of accuracy is sought, you can just use a Taylor series. Okay, so that I'm going to solve an example for that in the next lecture. And what I'm going to do is I'm going to look at the advection diffusion equation with a variable downstream weighting scheme. So here we had a variable upstream weighting scheme. I'm going to use this scheme for the advection term, and for the diffusion term I'm going to use this central scheme. Okay, and then I'm going to find the order of the accuracy or the truncation error of this approximation for this equation, and we want to find what is the order. Is it order delta x, order delta x squared? When will be that, right? And so if you have an approximation, this will give you a sense how you can calculate the order of approximation in any given equation, any given finite difference scheme that you might find. Okay, so this we will find it out in the next lecture, and after that we are going to go through the time marching schemes, time marching methods, and talk about time and evolution in finite difference methods. So let's review what we did today in this lecture. Okay, first we gave some remarks about the general method for approximating finite differences. So we said we need a requirement that the number of points have to be greater than the order of the derivative to be able to have a consistent finite difference approximation. Then we said if your number of points is one more than the number of exactly one more than the order of the derivative, then your approximation is generally order delta x, unless you have a central difference scheme in which it can go upper, like it can go to order delta x squared. And if your the number of points are greater than the order of the derivative plus 1, we can obtain higher order approximation by forcing fm plus 1 equals to 0, fm plus 2 equals to 0, and etc. Right? And then we solved an example. We expressed an approximation. We wanted to find an approximation for ds square over dx ds square u over dx square at I plus 1 using these 3 points: xi minus 1, xi, and xi plus 1. And so we wrote the general formulation for that based on the coefficients. And then the question was, what are these coefficients? Gamma I minus 1, gamma I, and gamma I plus 1. So we solved these 3 equations. So we had these qualities. F0, F naught should be 0 based on the consistency equation. F1 also should be 0. And F2 should be 1 because M here is 2. Right? Fm should be 1. So we obtained these equations, and And then we just simplified those equations, and we got we solved them. We solved those three equations, three unknown problem. And then this got we got this approximation based on this method. And then we try to find what is the order of error. What is the order of the error for this approximation? So we calculated F3, and we found it's not equal to 0. So this approximation is first order, or delta x. And then we said, if we use this for d squared u over dx squared, what's going to happen? And we found that F3 term is going to be 0, and thus this is going to be order delta x squared for d squared u over dx squared evaluated at xi. And then we said about this, if the approximation is given and the order of the accuracy is sought, we can just use the Taylor series, which we are going to solve it in the next lecture. Finally, we showed standard finite difference approximations that can be found from this method that we introduced. And I just wrote them down. So the forward difference, the backward difference, and the central difference, which is going to be higher order and if you use higher terms, you will get a higher order, like delta x to the power 4. And we also talked about we can combine these together by this alpha, multiplying them by alpha. So it's going to be like this one is a variable upstream weighting. So you can just do a weighting and combine these together. And this has some reasons that we might not go through them, like because of decreasing dissipation or other things in your solutions. You might do this. Numerical dissipation, I mean, not the physical one. And then we talked about d squared u over dx squared. We showed two examples, one in which we already had solved for that, and the new one, which is kind of more complicated. And it is delta x to the power 4. Okay. So as I said, next lecture we will talk about the example for finding the truncation error of the advection diffusion equation with two different finite difference approximations, and we want to find what is the order of that approximation. Thank you very much, everyone.